This is a demonstration of simulating and analysing serial crystallography data to show a use case for Jupyter Notebooks in the PaNOSC project, that's Photon and Neutron Open Science Cloud. Serial crystallography involves shooting tiny crystals of a sample into an X-ray beam and capturing diffraction patterns from them with a detector like an X-ray camera. In many of the thousands and thousands of images, the beam won't even hit a crystal, and when it does, that crystal could be at any angle. There could even be more than one. So processing the data requires both computational power and specialised code. If we want to try out some of that code, we can start by giving it simulated data. In a simulation, we can ensure that every frame has a clean diffraction pattern from a single crystal, so it's easier to analyse than data from a real experiment. You might do this to learn to use an analysis tool, or as a test case for analysis code that you're developing. For this simulation, we're using lysozyme, a small enzyme that's often used as a test case for X-ray crystallography. Its structure is available on PDB, the protein data bank, and that will be an input for our simulation. We're using a framework called Simix, which is also being developed as part of the PaNOSC project in Work Package 5. Now we start to configure the details of the simulation. First, the X-ray beam. This is where we set things like the beam diameter and the photon energy. Then the detector. Here we're defining a simple detector with one panel, 1000 by 1000 pixels, with each pixel 220 microns square. Then we add the sample details. You can see the PDB ID of our protein, and we're asking for each crystal to be 100 nanometers across. The other settings for now disable almost every possible complication for our simulation. Finally, let's run the simulation and have a look at the result. To keep this demo relatively quick, we're only generating 2 frames for now. This is one frame from our virtual detector. Those bright spots arranged in rings and arcs are what we're expecting, and they'll be the starting point for the analysis code. Let's switch to the analysis notebook now. I'm using some data we generated earlier for the analysis to save time. We now have 200 frames from the same 1000 by 1000 pixel detector. The pattern is different. This crystal was at a different angle, but we've still got similar bright spots arranged in arcs. We're going to be doing the analysis with IndexMajig, which is part of the Crystfile suite of tools. Let's start it running. We're taking advantage of the powerful computer we're accessing here to run on 80 cores at once, so it's done in just a few seconds. And you can see it's found crystals in all 200 of the images we gave it to process. IndexMajig records its output in a stream file. We can read that and examine the peaks that it's identified. You can see that in the first frame here it's found 67 peaks, got 67 rows in this peaks table, and if we draw those as little circles on top of the image, we can see it's found many but not all of the bright spots. We could try and adjust the analysis parameters to find more of those spots, but let's carry on with the notebook for now. For each frame, IndexMajig also estimates the size and shape of the unit cell, the repeating unit of the crystal. This gives us 3 lengths, A, B and C, and 3 angles, alpha, beta and gamma. We've got 200 estimates of each of these, so we'll plot them as histograms. And you can see that the estimates cluster tightly around specific lengths, 38 angstroms for this first one, and particular angles, which in all of these cases are 90 degrees. So this indicates that in this ideal simulation, we're getting good results. We can also fit a normal distribution for each parameter, and that gives us numbers which we could use for further analysis. For now though, let's see what happens when we introduce some complications to the simulation. So for this, we're starting with the data we generated in the first simulation. You can see one of the frames again from that here. We're just going to pick 2 random pixels from each image and set them to very large values, which could represent equipment faults, for instance. We've saved that to a new file, and here are the random pixels for that frame highlighted with red spots. This example really highlights the flexibility of notebooks. We've stepped outside the simulation framework, SimX, to modify the data directly with just a few lines of code. So we're not restricted to the options that somebody else planned for. We can easily do something different. Now, back to the analysis. We're running the same steps as before now, but with the noisy data. IndexMajig has finished, and if we plot the peaks that it's found, this looks a lot like it did before. But what about the unit cell parameters? These now look much messier. There's still a clear peak on the histogram where it's getting the right answer, the value that we'd expect, but there's also a scatter of results with very different values in each histogram. So even small changes to the data are already starting to affect our results. For the last part, we'll make one part of the simulation a bit more realistic. This is the Egypt 1M detector, which is used at European Exfil for serial crystallography experiments, and on the right there's an image taken by the detector. You can see that it's made up of 16 rectangular modules with gaps between them, and in fact each module has several smaller tiles. We'll set up the simulation with the X-ray beam as before, but now we'll generate an Egypt geometry, a specific positioning of these 16 modules. We'll save that geometry to a file, and we'll tell SimX to use that for our simulated detector. And now we'll run the simulation. And you can see now the output has gaps. We can only see the parts of the image where the detector tiles are located. Here's the analysis notebook again. Here's one of our simulated frames for the Egypt geometry, and let's start running IndexMajig. It's going to be slower now because we're giving it a more complicated problem. While it's running, these code cells starting with an exclamation mark contain shell commands. So this is a very convenient way to mix Python code with external programs like IndexMajig. Now it's finished, and here are the peaks that it's found in one frame, so you can see that the peak detection still seems to be working. And here are the unit cell estimates. We didn't add any noise for this simulation, but like the previous example, you can see a significant minority of the estimates are well out, so using a multi-panel detector like Egypt is likely to affect our analysis. We've shown here 3 rounds of simulation and analysis. You could easily go back and forth many more times, introducing different complications in the simulation and finding out how to adjust the analysis to cope with them. This flexibility is the real power of notebooks, along with remote access to a powerful computer to run the simulation and analysis quickly.